Hello students, in this lecture uh, we will be solving two problems in reciprocating compressor without clearance volume. So here is the question. A single stage single acting air compressor has a cylinder bore 175 mm and a stroke of 225 mm. The compressor sucks air at 100 kN per meter square and 27 degrees Celsius and delivers at 8 bar. Find the power required to drive the compressor if its speed is 120 rpm. Also calculate the mass of air compressed per minute and delivery temperature. The compression follows the law PV raised to 1.3 is a constant. So this is the question. This is our compression cycle. Okay, from 4 to 1 it is suction, 1 to 2 compression, and 2 to 3 delivery stroke. So this 1 to 2 double dash is the compression takes place in isothermal process. 1 to 2 is the compression takes place in polytropic process, and 1 to 2 dash is compression takes place in isentropic process. So air sucked through this process, it's a constant pressure process, 4 to 1, and in this problem the process is an polytropic process. So the compression process, the path of the compression process is 1 2, and the delivery process again a constant pressure delivery 2 to 3. Okay, so this makes a complete cycle 1 2 3 4, and it repeats. And the diameter and length, stroke length of the piston is given. Pressure P1 is also given. T1 is 300 Kelvin. P2 is 8 bar. Speed 120 rpm. And this is the equation for the polytropic process. And from this we can calculate the swept volume, that is the volume between top dead center and bottom dead center, which is equal to pi by 4 into d square into stroke length, that is 5.409 into 10 raised to minus 3 meter cube. This is the swept volume, or the volume at the end of suction stroke V1. Now for a polytropic process, the work done in a cycle is equal to n by n minus 1 into mRT1 into P2 by P1 raised to n minus 1 by n minus 1. See, we don't have this mass, so instead of this mRT1 we can use P1 V1, because for ideal gas P1 V1 is equal to mRT1. So use P1 V1 instead of mRT1. So P1 is 100 kN per meter square and V1 is the swept volume, because there is no clearance volume, so set volume is the volume at the inlet. Sorry, not volume at the inlet, it is the volume of air sucked during the suction stroke. So that is equal to 1.4435 kilojoules. So this is the work done per cycle. Actually this is 1.4435 kilojoules per cycle. But we want the power required to drive the compressor. So power is nothing but the rate of doing work. So this is per cycle. Then how many cycles are there in 1 second? That is kilojoules per second is the power. So indicated power is equal to work done W into N by 60, where N is the speed of the pump or speed of the crank. See, in one crank rotation, the compressor completes one cycle. So the speed of the crank is 120 rpm, then compressor completes 120 cycles. Okay. So if the work done per cycle is 1.4435, then work done per minute is equal to 1.4435 into 120, and work done per second is equal to 1.4435 into n divided by 60. That is this, which is equal to 2.887 kilojoules per second. That is 2.887 kilowatt. Now again, from our ideal gas equation P1 V1 is equal to mRT1, we can calculate M. M is equal to 6.282 into 10 raised to minus 3 kilogram. Make sure that all these units of P1, V1, M, R, T1, all the units are in SI units, should be in SI units. So P1 should be in kilopascal or pascal, V1 should be in meter cube, M should be in kilogram, R either joule per kilogram Kelvin or kilojoule per kilogram Kelvin, T1 in Kelvin. Now mass of air delivered per minute is equal to, this is mass of air delivered per cycle. So per minute there are 120 cycles. So M into 120, that is 0.7538 kilogram per minute. Then again the temperature at the point 2 or after the compression, for a polytropic process, the temperature ratio is equal to P2 by P1 raised to n minus 1 by n. From this equation, we will get T2 is equal to 484.759 Kelvin. Okay. This is the first problem. The second problem is, an air compressor receives air at 1.2 bar and 18 degrees Celsius. It compresses the air to 8 bar. Calculate the heat transfer and work done per meter cube of air taken in the cylinder when the air is compressed adiabatically, isothermally and polytropically. For polytropic process, PV is equal to 1, PV raised to 1.25 is equal to a constant. This is the question. So let's look at this data given. P1 is 1.2 bar, T1 18 degrees Celsius, which is 291 Kelvin, P2 is equal to 8 bar and V1 is equal to 1 meter cube. This is not given, but we have to calculate all the heat transfer and work done per meter cube. So per meter cube of air taken in the cylinder. So we assume that P1 is equal to 1 meter cube. Okay. Now the first case, when the air is compressed adiabatically. See, adiabatic, reversible adiabatic or isentropic process, we have already derived the equation gamma by gamma minus 1 P1 V1 into R, which is compression ratio raised to gamma minus 1 by gamma minus 1. This is the work done for adiabatic process. So here this compressor is an air compressor. So gamma for air is 1.4. Then substitute all the values and you will get adiabatic work done is equal to 302.9 kilojoule per meter cube. Now, what about the heat transfer during adiabatic process? See, adiabatic process is the process in which there is no heat transfer from the system or to the system. So, the heat transfer Q will be 0. The second case is when the air compressed isothermally. So work done is equal to P1 V1 ln P2 by P1, okay, which is equal to 227.65 kilojoule per meter cube. Now heat transfer for an isothermal process. See, in isothermal process the temperature remains constant. So there is according to the first law of thermodynamics, dQ is equal to du plus dW, and du is the change in internal energy. So change in internal energy is a function of temperature, and the temperature is constant, then there is no change in temperature. So du or change in internal energy will be 0. That means in an isothermal process the heat transfer is equal to work transfer. So Q is equal to W, which is equal to 227.65 kilojoule per meter square. So meter cube. Now the third case, when the air is compressed polytropically. This is a polytropic process equation for work done, and the work done in polytropic process is 276.865 kilojoule per meter cube. Now heat transfer during polytropic process is equal to work done in polytropic process into gamma minus n by gamma minus 1. So how do you get this equation? This is from your basic thermodynamics. From first law of thermodynamics, dq is equal to du plus dw. So for polytropic process, you know that dw is equal to p1 v1 minus p2 v2 divided by n minus 1, and dq is equal to, what is du? Du is change in internal energy, that is mcv dt, and plus p1 v1 minus p2 v2 by n minus 1. So which is equal to, instead of cv we replace cv with in terms of r and gamma. So cp by cv is equal to gamma and cp minus cv is equal to r, and using these two equations we will get a expression for cv, which is r by gamma minus 1. So m into r by gamma minus 1 into dt plus p1 v1 minus p2 v2 by n minus 1. Now what is dt? dt is t2 minus t1. So mr t2 minus mr t1, that is p2 v2 minus p1 v1 divided by gamma minus 1 plus p1 v1 minus p2 v2 by gamma minus 1. Okay. So now if you replace this p1 v1 minus p2 v2 here and multiply this with minus, then p1 v1 minus p2 v2 by n minus 1 minus P1 V1 minus P2 V2 by gamma minus 1. So finally we will get P1 V1 minus P2 V2 by n minus 1 into gamma minus n by gamma minus 1. This is the equation we used in our problem. This is work done in a polytropic process. Now substitute all these values. We will get 103.824 kilojoule per meter cube of heat is transferred in the process. Okay. In PV diagram, see 4 to 1 is suction, 1 to 2 dash is isothermal compression, 1 to 2 is polytropic compression, and 1 to 2 dash, this dash is adiabatic or isentropic compression. Now in next class we will discuss about reciprocating compressor with clearance volume.